prevent drifting in his sleep. How will man's subconscious mind react to his first experiences with space travel? Will he not suddenly be aware of his precarious situation, trapped in a tiny metal box, floating through the incomprehensible nothingness of space? We do not know. We must plan intelligently if these pioneers of space are to survive and return to Earth safely. The conquest of space will depend to a great degree on the research and findings of this important new field of science, space medicine.
To the engineer, spaceflight poses two problems. The first is, of course, to build a rocket ship. The second, and no less important, is to prepare and train the men who are to fly the future rocket ships and to provide suitable working conditions that will enable them to survive in space. To help show you what is being done to solve these problems, we have called upon one of the foremost exponents of space travel, Dr. Werner von Braun, who is at present the chief of the Guided Missile Division of the Army's Rocket Center at Redstone Arsenal. He was also overall director of the development of the original V-2 rocket.
The training methods for future space flight and the special equipment needed for survival are much like those of present high-altitude flying. And the experiments we are making today are helping us to solve the more complex problems to come. Take the present-day pressurized flying suit, for example. It has been designed for use at extremely high altitudes and is a forerunner of the suits we will wear when we make that trip to the moon. To give you an idea of how engineers and medical men are working hand in hand, here are a few examples of the research that's being conducted at this time. This pressure suit is being worn in a test chamber where the air pressure can be dropped suddenly. Notice that the water boils at this low pressure, even though it is only at normal body temperature. Blood would be the same without the protection of the suit. In other tests, without the suit, where the drop in air pressure is less severe, we see that the body still reacts violently to a sudden decrease in pressure. Lieutenant Colonel John P. Stapp of the United States Air Force has subjected himself to the tremendous forces of a rocket sled that reaches a speed of over 632 miles per hour. The sled stops so quickly that Colonel Stapp's body becomes 35 times heavier than normal. From these tests, we have learned that men can take much greater acceleration forces than crew members of a rocket ship will undergo on a takeoff. Today's aircraft are so fast and so complicated that it has already become routine to train the crews on the ground without risking lives or equipment. This is done with a device called a flight simulator. Here the crews experience all the sensations of an extended flight. The crews of future rocket ships will train much the same way. We will use a simulator on a centrifuge and employ an astrosphere to train the celestial navigators for our coming space flights. Now here's a model, my design for a 4-stage orbital rocket ship. Compared to the unmanned instrument rocket, it is quite large. But the overall size and weight of the rocket is mainly determined by the 11 tons weight of this top section. This weight dictates the amount of fuel and the numbers of motors needed to produce enough power to equalize the gravitational pull of the Earth. The payload in the top section will consist of 10 crew members plus equipment. Notice the wings, small rocket motor, and landing gears. This is a section that must ultimately return the men to the Earth safely. To produce the energy needed to hurl this stage into the orbit, we need these 3 additional rocket-powered sections. Here we have a cutaway drawing of our rocket, showing the location of the fuel and the motors of each section. The first stage carries 1,060 tons of fuel and its 29 motors will lift the entire weight of the ship vertically off the ground. The second stage has 8 motors and carries 155 tons of fuel. It will be dropped when its speed has reached 14,300 miles per hour. The next is our third stage, with only 1 rocket motor and 13 tons of fuel. The third stage gives the passenger section the final kick to attain the orbit. It will not be separated from the passenger section until just before the return flight. The third stage will be left in space, and a very small motor in the winged fourth stage will return the ship to the atmosphere so it can glide back to the base. If we were to start today on an organized and well-supported space program, I believe a practical passenger rocket could be built and tested within 10 years. Of course, it would be foolish to rush headlong into building a 4-stage rocket, man it with a crew, and attempt to fire it into an orbit without first following a step-by-step research and development program. Let's illustrate this with the help of a few pictures. First, we would design and build the 4th stage, and then tow it into the air to test it as a glider. This would also allow the crews to practice. Next, low-altitude flights would be made, firing the small rocket motor in the 4th stage. This would also give the crew more and more training. Following that, the 3rd and 2nd stages would be constructed and tested very thoroughly on the ground, after which they would be joined to the passenger section so that faster and longer flights could be made up to speeds of about 12,000 miles per hour. The only thing remaining would be the building and ground testing of the huge 1st stage. Then there would be no more test flights. When all the sections are joined together, the ship and its crew will be ready for man's first flight in space. Let's look ahead a few years and see how this might be accomplished.
There it is, a small atoll of coral islands in the Pacific, where man is dedicated to just one cause, the conquest of space. Here below us, a small city has been created to house the scientists, engineers, and technicians on whose shoulders rests the tremendous responsibility for this great adventure. This is the Rocket Assembly Building, with tracks running to the launching site. Only 48 hours remain until firing time. Our spaceship moves ponderously toward the firing site. After the ship is securely anchored over the blast tunnel, the elevator spar is raised into place for the final pre-flight check and fueling. This is the blockhouse, the control center for Operation Space Flight. Here, the oscilloscopes, radar scopes, computers, and tracking devices are the brain and nervous system for the rocket. Dancing patterns of light will record every detail of the blast-off and climb into space. In the windowless blockhouse, observation is by periscope. Through a system of worldwide radar stations, electronic eyes will always be focused on the rocket as it orbits around the globe every 2 hours. The tracking radars report ready and are standing by. The optical tracking stations are poised and ready to follow the rocket in its upward flight. As 0 hour approaches, the painstaking work of the checkout crew continues. The ship and every piece of its equipment is being checked and rechecked.
Blockhouse, can you hear me? Will you give me that stage 2 separation signal again? Okay now, over. swivel motor, state straight, and pitch right. Okay, now give me the left.
Attention, all personnel. It is now X minus 2 hours. Fueling crew, take your stations. Safety area will be cleared by all personnel.
In the pits, the required quantity of fuel is preset. The pumps will deliver 1,230 tons of hydrazine and red fuming nitric acid into the tanks of the waiting rocket. It is now X minus 20 minutes.
Flight crew, report aboard rocket. Flight crew, report aboard rocket.
After years of careful preparation, testing men and materials, this is the final payoff. Now, man will bet his life against the unknown dangers of space travel. Human reactions are not precise enough. Therefore, once the launching timer is started, the entire takeoff and flight into outer space will be controlled automatically.
X minus 5 minutes. Clear the firing area. Clear the firing area.
X minus 90 seconds. X minus 30 seconds. X minus 20 seconds. X minus 15 seconds. X minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
The total firing time has been 5 minutes. The ship will now coast for 51 minutes before the adaptation maneuver begins. At over 60 miles above the Earth, the crew members experience the sensation of weightlessness for the first time.
Blockhouse to XR1. Your cutoff altitude is 63.9 miles. Distance from launching pad, 705 miles. Velocity, 18,467 miles per hour. Angle of elevation, 4 minutes apart. Plane of your ellipse of ascent incline, 66 degrees, 32 minutes, 2 seconds to plane of equator. Out.
51 minutes later and halfway around the world, the rocket is coasted to its maximum altitude of 1,075 miles. Its speed has diminished to 14,770 miles per hour. The navigator must now take a bearing on 2 fixed stars. He will line up the ship for the adaptation maneuver, which will drive it into a circular orbit around the Earth. The electronic controls will fire the rocket motor at the exact second the ship reaches the proper position. The ship and crew are now coasting freely and silently through space. Here, man is no longer earthbound. From his new vantage point of over 1,000 miles high, he sees the Earth as a vast rolling sphere, upon which the oceans and continents are reduced to simple patterns of light and dark. Great cloud formations will appear as small patches of snow. Evidence of man's existence is almost invisible. Large cities can be seen only with the aid of powerful optical equipment. meteorologist will make studies for